Hello and welcome back to the lecture on applied econometrics. So in this lecture we are going to talk about
autocorrelation, and in this lecture we will try to understand autocorrelation mathematically, and it is going to help us in understanding the consequences of autocorrelation. So we'll do a little bit of maths here. Now in the previous lecture we have seen how actually if we have autocorrelation how it will look like. So we'll see some sort of pattern, right? So if we actually plot this ACF with the lags, we can actually observe this sort of pattern here, right? Now this pattern could have different shapes, and we could actually have some idea about these patterns, but one thing we need to remember is that we're actually plotting the correlation coefficient, and the correlation coefficient always varies between plus 1 to minus 1. So we can expect the ACF to vary between plus 1 to minus 1, and therefore the pattern that we will see, it will play in the range of plus 1 to minus 1, right? Now if we think, let's do an intuitive thinking, and let's say that we just plot similarly the ACF here, ACF on the y-axis and the lag on the x-axis. Now I'll write lag and ACF. Now a simple point I want to make here is that if I have, let's say in one period I have my ACF is close to 1, let's say, but as I move in time, as I actually progress in time, what will happen is that the impact or the correlation of what happened here and what will happen here, they actually tend to decrease. Like as the time progresses, it is an intuitive thinking. As the time progresses, whatever happened in the past, the impact of that is going to be less and less and less, right? Now, so that is basically, usually we see this kind of, sort of um, plot. It can also be, it can actually oscillate, like there could be a lot of cyclical, seasonal or cyclical patterns, so where we will see that the ACF to vary between plus 1 to minus 1. So these types of relationships, these types of plots you will see time and again when we plot ACF with lag. Now the point is, of course, with ACF we can understand if there is autocorrelation, but what more? Is there anything more? And there is something very interesting about this, is that we can actually identify if the autocorrelation is significant. So essentially, it can also help us to test if this autocorrelation is significant or not. Now, how we actually use this ACF and lag plot or correlogram plot to actually identify if the autocorrelation is significant or not. So let's just think intuitively without getting into any complexity. Let's just think, let's say if the correlation coefficient between two successive time period is actually less, then perhaps the autocorrelation is low, right? So that means the error terms are not, perhaps the correlation coefficient among the error terms are actually low. So they are not, highly related. So then if the correlation coefficients are low, then perhaps I can say that, well, autocorrelation is not that much. And to actually have some uh, benchmark or some sort of threshold, we can actually have something like this. So let's say if the correlation coefficients between two successive periods is actually lying, or is actually lying between this range, let's say all the ACF values are lying here, it can go either side, but it is, the range is always constant, it's fixed. So as long as the ACF values are this low, so then I would say that, well, perhaps the autocorrelation is not that high. But if it exceeds, if it goes in this zone, in these regions, or in this region, so then I'll say, well, so the autocorrelation is actually a little, there are autocorrelation present, okay? So we need to really talk about that. Now, one test that we do is called Burlett's test. So the test we do is called Burlett's test. So it actually uses the same idea, where we have some sort of threshold value for the correlation coefficient, and if the correlation coefficient is more than the threshold value, then we say that, well, the autocorrelation is significant. And for Burlett's test, if we actually identify the ACF, the correlation coefficient as rho, and k being the lag, and if we have rho k is the value of the SCF, it will follow a normal distribution of 0 mean and 1 by n standard deviation variance. Okay. Now, where n is essentially the sample size, n sample size. All right. N is the sample size. Now, this is essentially, if you can see that it is actually depending on the sample size and nothing else. Okay, and I'll just explain intuitively why this is the case. If we have large n, if we have large n, for large n, what we'll have is that the standard deviation is going to be low. Sigma is low, right? For small n, the sigma is going to be high, right? For small n, sigma is going to be high. Now, it means that for large n, I'm going to see very low variation. So with large sample size, I'm going to see low variation. And now related to the previous diagram, so with large n, so the more lags you have, with large n you will have more lags, and the more lags you have, it actually, the impact of previous periods, actually it is sort of coming down, right? Because you have, a lot of time periods have elapsed and the effect has been reduced. Exactly the same here in Burle's test. With large n, we will have a lower standard deviation, whereas for small n, I will have the standard deviation high. Okay, so with this, we can actually do some sort of um, estimation of whether my autocorrelation is significant or not. Let's say I have, I have an n of 100, and my 1 by n, which is, let's say, sigma square is 1 by n, so which is 1 by 100, so which is 0.01. It would mean sigma is equal to 0.1. Okay, so now if I want to have a confidence interval, if I want to have a you know confidence interval with 95% with alpha equal to 0.05, so then the confidence level is 95%. So if I want to construct a confidence interval, so then how it will look like is that it will look like mu minus 1.96 sigma, the rho k value. I'm basically creating this confidence interval for rho k. So it will be mu plus 1.96 sigma, right? So it means my sigma is equal to 0.1 and my mu is 0, but let's test follow 0 mean. So that would mean it would be 1.96 into 0.1 rho k, and here also 1.96 into 0.1, so that would mean minus of 0.196 to plus 0.196. Okay, so as long as my rho k is in this range of minus of 0.196, so according to our diagram, let's say this will be 0.196 and this is minus of 0.196. As long as it is in this range, what I will have this threshold, and as long as my rho k is falling within this, I would say there is no significant autocorrelation. But if the autocorrelation is higher than this, say perhaps 2.2 or 0.2.5, so then I would say yes, autocorrelation is present, and this is simply determined by n, and here is 100. Okay, so depending on n, I can actually construct the confidence interval. Of course, I have to have the confidence level or significance level. Okay, so that's what we understand by the Burle's test. Now, one thing we have to remember, and that is very important to understand the autocorrelation process, or we say, how the data is being generated when the autocorrelation is actually determined. So we can actually model that, and we can model the autocorrelation using the concept of lag. So modeling autocorrelation with the concept of lag, okay, of lag. Now, why is that important? Why this lag thing is so important to model autocorrelation? I'll just talk about that. Now, if a disturb, so basically what we are talking about, when we talk about autocorrelation, what we mean really is that the error term of a tth period is actually related to error term in t minus 1th period. Okay, so now to what extent this relation extends? Okay, so is it extending to only one period? So can I write, let's say, if yt, let me write it down, yt is equal to, or actually I can use a different color. If yt is equal to beta 1 plus beta 2 xt plus ut. Now I have my error term ut, and I said that this error term is actually related. It is somehow related with the previous period error term, which was ut minus 1. Okay, so I can also write yt is equal to beta 1 beta 2 xt minus 1 plus ut minus 1, and I'm claiming that ut and ut minus 1 are actually related. So then I can actually write down ut is equal to, let's say I use some other coefficient, let's say rho, of course, because this is the correlation coefficient between ut and ut minus 1, ut minus 1 plus some et. Now this et has to be IID, et has to be completely independent of the whole, all the variables. Okay, so et follows IID, et is IID with mean 0, 0. Now with this I can actually explain the autocorrelation. I can actually say this autocorrelation is actually one, it is dependent on only the past period. Okay, only one past period. The exactly just the past period is actually influencing the present period error term. So I will say this is auto-regressive autocorrelation of order 1. Of order 1. So what I mean by that, I'll explain that. So the order 1 is understandable. Order 1 is just meaning that it is dependent on just the past period. Now what is this autoregressive term? What is this autoregressive term? Now regressive, the moment we say the word regressive, so here what we see is that we can actually predict ut. We can actually predict ut depending on the past period value of the error term, which is ut minus 1, and we actually have an innovation term here, a randomness component here. So essentially you need to regress to actually get from ut minus 1 to ut, right? So that is where the regressive term is coming in. And why it is auto? Of course, we know what auto means. Auto means, self. So it is regressing with oneself. So which is again making sense because ut is regressing with itself. It's but the past period value. So ut is regressing with ut minus 1, and that is why we call it autoregressive. Autoregressive autocorrelation of order 1, or in short we write it AR1 process. This is something we call AR1 process. All right. So this is now, if suppose instead of ut being determined just by one period, let's say ut is determined by maybe 2, 3 periods, 4 periods. So how do I write that? So let's say I'll use a different color here. Let's say ut is getting determined by rho 1 ut minus 1, rho 2 ut minus 2, and maybe I don't know, rho 3 ut minus 3, and then you have an innovation term, of course. So this one you write as AR3 process because ut is getting determined by 3 period errors. Okay, So this way you can have AR5, ARN, whatever order you want. So we usually write ARP. So autoregressive autocorrelation of order P. All right. So this is how we'll understand the autocorrelation process. Now, another way of understanding it is that when we actually represent the autocorrelation in terms of the moving average. Okay, so let me write it down. Moving average autocorrelation. So how we represent a moving average autocorrelation? This is a simple process where we actually represent the error term in terms of the weighted sum of the past period and the present period error terms. Okay, so we will write it as, let me use a different color, or I'll use the same color. Let's just do it. So let's say it is represented as t lambda 1 t minus 1 lambda 2 t minus 2. So essentially it will be a moving average we represent as MA. It's a MA2 process. Is the MA2 process. Whereas the MA3 process will be where I will represent UT is equal to lambda 0 t lambda 1 t minus 1 lambda 2 t minus 2 plus lambda 3 et minus 3. So this actually is a very brief representation of time series data, how we construct a time series data. We are not really discussing at length this AR process or MA process. There is plenty of discussion of how AR and MA process pans out and how AR MA together pans out, so on and so forth. So we're not getting into that. We're just introducing you this concept of AR and MA because we want to actually show you in the next lecture the consequences of autocorrelation, and to explain that consequences we need to use this mathematical formulation. So with this we end this lecture here. Thank you.